Christian, and thank you very much the whole iBAT team, Andreas Hutter and Andrea Baumann and Christian Ochsenbein for organizing these nice Battery Tuesdays, because it's a nice chance to get to know all the different partners in iBAT and around batteries. So yeah, it's a pleasure to be here. And yeah, what we're gonna do today is we look a little bit into what we can offer at Battronics. So we are basically a company that is doing battery technology, patents, and aging analysis. And today we also dive a little bit more into the aging analysis of batteries. And we are located in Switzerland with our main office in Zurich, and also in Germany and in Poland with subsidiaries. Okay, what the first topic that we do is we do basically the main problem today is that there's so vast knowledge outside, and there's like more than 250,000 patents and theses and all research analysis done outside in this world. And every company needs to basically do research to stay like up to date and innovative in the field and with competitors. And here that's really what we do, because the problem is that this data that exists all in the world is very, very time consuming. So there's 140 patents coming out on lithium-ion batteries per month. And so it needs already 7 highly skilled PhD to just read and sort through them. And that's really what we want to do, like do this tracking. And what we really like, our main goal is to avoid research. Like the word research basically means like replay or rebound or something, means basically to search again. That implicitly means that somebody else has done it before the word research. And this is exactly what we want to like try to minimize. We want to do all the pre-search that is available already on existing data and help our customers basically to avoid doing research and basically do like new innovations. And that really helps our customers to save time, save costs, and also give a competitive advantage, because one can develop new patents and new solutions for the market. And we really do that in all different fields. We do that in aging analysis, in modeling, periphery, in production processes, in like dry coatings, in new pack designs, in new anode or cathode structurations, and so on. Like basically from chemistry up to engineering level, we support companies in these innovations and in solving the technology changes. Okay, that's basically, how can you imagine that? What we really do is we puzzle this knowledge all day. So we basically take, let's take an example. What we really do is we take, for example, here a puzzle piece from how in theory lithium would intercalate in graphite, how the stages would form and so on. Then we really would superpose that with another puzzle piece from another source. For example, in this case here, it's just as an exemplar, like an example, it's a it's a graphite particle with an SEM image taken, and then we superpose and combine these two information pieces together and show how these phases would basically form in graphite. And basically with these phase formations, we can then show why graphite cannot be charged so quickly nowadays, but can be discharged, for example, extremely rapidly. So it's a very asymmetric material. And this is basically what we do. We puzzle this knowledge from patents, from data sources, from teardowns of battery data, and so on. Okay, and with this, we really help to make the very comprehensive technology, patent, and market analysis. So we basically cover usually these 3 aspects when we cover a new technology, be it dry coating, like be it cell to pack, and so on. We do this like this analysis around it to help basically our customers, as we just said before. So this is our first part. This is all the technology and patent and market analysis that we do. And that's really like what we do as a consulting business. Then the second pillar where we usually help is aging analysis. And that's also the focus of our presentation more in a deep dive today. So we look a little bit into this aging. And many of you that work on batteries probably already had to do with aging data to predict the lifetime of your application that you're building, be it an electric vehicle, be it a drone, be it a scooter. And they have all different specs that they have to fill, like how long to operate, how quickly to charge, and so on. And this obviously has an impact on battery aging. And here we want to help companies to do these analysis automatically, again, to save time. And also have access to all these existing data sets on commercial cells that have been already tested elsewhere. So to avoid, again, researching the same battery cell. Exactly. So that's basically our goal. How do we do that? So here I brought you an example of a very prominent example. It's the Nissan Leaf. And many things in aging analysis are very complicated. And that's what I want to show here on this example. For example, you had the old Nissan Leaf. The old Nissan Leaf was built roughly from 2011 to 2015. And what you see here is the aging of the fleet, the roughly 100,000 electric vehicles of Nissan Leaf that were sold each year and then were driving in the field. And here you have this data from like a customer data set, how these battery packs in the field, basically driving in New Zealand and in Japan, aged over the time. And what you can see here is basically the fleet, an average when you have a high scatter, but the average fleet lived 5.6 years until reaching 80% capacity. So let's be honest, that's not the best case scenario for everyone as us as a customer. If we would be on the customer side, 5.6 years for a car is not a too long aging, but it's at least longer than the warranty of 5 years, here marked as a red point. And then Nissan Leaf updated the battery. So they upgraded the battery to 30 kilowatt hour in the same space, and they have a very good engineering team and everything, and they designed quite good this battery also. But what they seem to have overlooked is the aging that changed. And what you see here is that the new cars that were released from 2016 to 2021 had this upgraded 30 kilowatt hour batteries, and the whole fleet, again, this 80 to 100,000 Nissan Leaf that was sold per year, aged now after 2.4 years already to 80% capacity. And this is obviously like the worst case scenario you can have as an OEM, to underestimate the aging that will happen in the field. And this is exactly what we want to help customers with, because it's so difficult to analyze aging. And there is a lot of knowledge outside with different aging analysis and machine learning and so on, but it's still a very, very delicate problem to estimate field behavior. And here, that's where we at Battronics support and develop this aging database. So maybe I walk you a little bit through it. What we then developed is like this aging database together with the Berner Fachhochschule. And here we want to make advanced visualization to also make predictions, show what is happening, how we can change the use case. We make physics-based aging prediction on the one side and machine learning assisted aging prediction on the B side. And at the end, when everything works, we want to have a battery recommender that you can have basically your use case. And from the database, it makes the reverse search to basically look what's the optimal battery for this use case from the existing database. How will this look? This is here a mock-up of like how this looks. So you have basically measurement data that looks relatively noisy. You see it here, the capacity fade, how it's going down. And then we do the prediction with these two different methods to basically calculate the remaining lifetime of this battery. That's basically, that's what we do. And currently, we have already our minimum, our pilot running in the internet. And what is here doing is like, maybe I just show you because it's a video. I hope it's running. I have to share the.
For the moment, we still see the presentation.
Yes, wait.
We already began to upload commercial battery data to the database. Currently, we have 217 batteries uploaded so far. Here you can see and select single battery cells. You can also view it grouped per type. Here we can see the aging data versus the cycles. And here we can see the aging data versus the voltage.
Okay. Maybe I stop here. And what is then nicely, so this is currently what we upload in the database for reference data, first of mainly commercial cells, like you may have seen like Panasonic, LG, and 123. Basically, what the suppliers we all know. And later on, what we will have here is, or like what is already offline working, is a login area where then you can upload your own data and you don't share it with us. So it's like very important. And you can basically make the aging prediction with your own aging data that you have, basically. Exactly. So this is the aging data analysis that we supply basically for supporting these aging analysis. Then we also want, as a wanted to look a little bit into aging matrices, because obviously it looks very how would I say, like very helpful to do this aging analysis. But the main problem is that the data that you have for aging analysis is quite, let's say, quite different. And let's look a little bit into these aging matrices. So one, you have usually, let's classify them in 4 different sources of aging. And one is like a simple aging test. Usually you get it in the data sheet from the manufacturer. That's like usually like 1 to 12 pages of data sheet where you have like cycling data, rate test, and so on. Then you have relatively elaborated laboratory test matrices, and there it's very nice because you can separate in calendar aging and cyclic aging quite well the tests. Then you have, as a third point, you have repeated pattern cycling, we call it always. That's usually used then for machine learning data training. Because you need some features that appear like more frequently, or you have some data where you can train on. And the worst data set is obviously the randomized aging. That's usually coming from driving profiles when you have data directly from use of field data, because it's like going from all over drive profiles to reduced data sets like histograms, or like even more reduced data sets where you just know a few data logs during lifetime. It depends a bit on the BMS. And let's go a little bit through these different data sets. And here, for example, this is the simple test that's, for example, in a data sheet, just standard cycling, for example, 1C, 1C, 100% depth of discharge, room temperature, and you get a cycling curve, and you see that's basically, 1,700 cycles, you would still live at 93, 94% capacity. So it's a quite decent and nice aging, right? It's relatively only 7% aging roughly after 1,700 cycles. However, we never have in the field 1C, 1C and room temperature. And especially we never have 100% depth of discharge, because most batteries in the fields are never depleted to 0% SOC. So this data helps us obviously very, very little in making predictions about the use case scenarios. Let's go to the second case. Then this one is like laboratory test matrices. And here I brought in a very nice example of Michael Schimpe and co-workers that was published. And what I just use it as an example because these data is extremely nice, because you have, like, for example, here 9 different SOCs and 6 different temperatures where you measure just the calendar aging, and then different rates with CC and CCCV, so constant current and constant voltage, another rate test for making the cyclic aging test. And then what you basically get nicely, you get these different aging data, which you can then analyze, split, and separate into aging mechanisms to to understand this battery. And this is obviously the positive things about it. It's very, very good for us humans because yeah, the data is very structured. We try to cleanly separate calendar aging and cyclic aging. However, the analysis is usually relatively tedious because you have a lot of data that you have to analyze, clean up, and so on. And it's also blocks you a lot of test channels because, as you can see, you have just 9 times 6, like 54 channels already blocked for making this calendar aging test, and then and having only one repetitive cell per SOC and temperature. While here for the cycling test, you have maybe sometimes already 3 cells, but still you block, like in this case, probably like 54 plus maybe 30 here, like 80, 90 channels for a period of, in this case, 250 days, so like almost 10 months. And this means it's a relatively expensive method from testing because you need so much data to separate it nicely. And then obviously, this is quite nice, as I said to you already before, like for human-based analysis. And then you have the third data. This is more like randomized, not randomized data yet, but it's like, yeah, you look on certain features in your curves. So you still do different testings. In this case here, this is the MIT thesis of Kristen Severson. And what you see here nicely is it's a lot of cycling data of the very same cell that we saw on the spec sheet before, the A123 cell that we just discussed on the data sheet. And yeah, you do then the data analysis to do aging prediction. However, the main thing is it's very, very good once the model is trained. And then after you trained it with a lot of data, afterwards it needs only little data. However, you don't get really an insight what happens in the cell because you make, like in this case here, machine learning level 1, so stochastic feature fit. Yeah, and on of variances of certain features, but it still helps you because it's like the most once you train your data set, it's a very rapid method and gives you also relatively good and relatively reliable feedback on your future aging. Exactly. And then the last one is the randomized data, and we just had this example before. That's why I repeated like here. It's like from driving profiles, and there you really have like scarce data. It's like really you have only a few data points and so on. And this is like one car tested basically when they go to the garage and read the BMS out. Then you get the capacity data basically logged by the customer. So it's like very, very little data, and you can learn very little, but yeah, you still need to analyze it because that's your driving profile, right? Like VLTP driving profiles and so on. And what we do really at Battronics, that's what we now in this database try to combine to really make use of these different data analytics, to bring them in, to basically bring use case 1, 2, 3, the data sheet, the physics-based and the machine learning-based in to help predicting this field data, number 4, basically. And this is really what we like develop in this aging database, yeah, to help, yeah, this number 4 use case, the field data prediction. Okay, then I come to the third point that I wanted to show, and that is, yeah, it's a bit a different topic. It's on the IPCEI. So the IPCEI is means important projects for common European interest. And there have been very nice presentations of Andreas Hutter already in March and in June last year. I don't know if many of the participants in the audience today have participated in this. So it's a very nice opportunity because what we from Switzerland, from the iBAT members now could do, we could apply as associated partners. And that's why I brought this today also to show you what, yeah, how you could apply also to this. So there actually exist two IPCEIs for lithium-ion batteries. There exist also other IPCEIs two for hydrogen infrastructure, one for microelectronics, and so on. But the two for us as the iBAT are important are the IPCEI on batteries, here on the left side, which you can see here with the partners. That's governed by the French consortium. So it's a French-led IPCEI. And there's a second consortium, it's the IPCEI on European Battery Innovation, in short, iBAT-in. And here you see the second iBAT-in, which is mainly governed by the German Federal Institute, basically by the VDI. And here you see like the important project of common European interest, obviously mean already by the title that these are very important projects. And you see already the partners here, Northvolt, SGL Carbon, Arkema, BMW, and you read all the important names basically from raw materials and advanced materials as the first pillar, battery cells, obviously, as the second pillar, battery systems, and recycling and sustainability. And this, like in 2023, in the autumn, in November, it started basically that first partners could apply for this IPCEI iBAT-in, so for the second part here, to be an associated partner. And we as in Switzerland are eligible now to apply for this associated partner. And that's why, yeah, I also brought you here nicely, like an overview of what requirements and also how the procedure works. That's what you have here. So basically companies and research and technology organizations can apply that want to become an associated partner of iBAT-in, and they must prepare for this preparation basically a sheet that Andreas Hutter can also nicely supply, because Andreas Hutter made all this possible, and application also, yeah, he can give you access to this sheet. Basically, you fill your company or RTO information. Then you need to be an EU member state or EFTA country, and obviously Switzerland is an EFTA country, so we are eligible from Switzerland. Additionally, now it becomes more complicated. So there's the first part is probably easy, and then the associate partners shall already participate on ongoing or planned project with at least 2 collaboration partners from the IPCEI iBAT-in. That's why I brought you the list. So basically, you need to have an existing project with 2 partners here from this project. It can be mixed from different categories and so on, but it needs to be 2 partners where you work together. And then get a letter of intent to also collaborate further. I continue. So, and then it must be either in a research stage or already in a further processing stage. It should, the whole project which you apply and which contributes to the partners, to the direct partners, as you just saw before, should have not started earlier than 2 years prior to the submission of your application. And also they have to contribute to the common goals of the iBAT-in. So this is the 6th requirement. And the most difficult is actually the associate partners should have received for this project, which they have already 2 collaborations with partners, already at least 1 million European funding from national authorities. So in Switzerland, that's basically the Energy Office or the InnoSwiss. And then basically you can apply to the organization committee to basically become an associate partner. As an associated partner, you basically can participate in network meetings, but you cannot vote, obviously, and so on. It's basically to communicate, network, and help the European supply chain to grow also from outside, from inside of Switzerland for all our European member states and neighboring countries. So this is the 3rd topic that I wanted to present. And then yeah, I wanted to thank you very much. And yeah, I'm open for many questions that you might have on either pattern technology or aging analysis, or also on the IPCEI iBAT. And we hope that in the future we can also work together to puzzle all these different technologies together and help you basically solving difficult science and tech issues in batteries. Thank you very much.
Well, thank you very much, Michael, for this very interesting presentation. Please, for the audience, either raise your hands or write into the chat the questions you have. Maybe for the start, you showed us this puzzle with the first slide, and I think also with the last slide. And do you see, like, from this puzzle, some major trends or some very new trends which came up in the last few months that maybe you can give us a glimpse of that work? Or
so yes, so currently it's like mainly from technology wise, you mean, right? Not from market, right? Yeah, technology wise, you see really the recoming trend, like let's say on the active materials. There's really two trends. One is coming, the so far thought dead materials come back. One thought dead material is LMFP, for example. LMFP exists since 1996, and also there have been a Swiss battery startup near Lausanne that worked very heavily on it. It was later on acquired by Dow Chemicals, and so this was like, oh my God, this was like in the 2009 to 2000, around this time. So like 15 years ago, basically people worked on it already, also in Switzerland. And now there's a revival, just like we had a revival on LFP like 4 years ago in China, and it's shortly swapping also to Europe now, or like slowly swapping to Europe. We have the same like with LMFP, which is also now reviving in China. And this is just pure like guessing now, because there is not yet so much indication, like commercial wise, will swap also to Europe. And for US, it might swap already because Tesla may like currently qualifies it from CATL, the new M3P cells. So basically, this is like, there's always like, this is like research, right? Where the technology is like 1996 is like 27 years old, 28 almost now. And it's coming back suddenly, and also makes it into premium vehicles, probably of Tesla, for example. And this is something like, yeah, it's like all the knowledge has been there already for many years, and suddenly it makes sense for like other factors, like in this case, cost versus energy and so on. Then other factors are not like, there's many active material topics also on the nickel-rich chemistry, more manganese chemistries, on the anode side, and so on. But when we go away from the individual cell components, there is like these new packaging designs and how cooling and packaging can be nicely integrated. That basically is known as like very efficient packaging technologies that exist all over the place, that we basically design the cells so that they can be nicely packed and cooled. So usually that makes the cells quite long, or like blade batteries and so on, or Dragon battery. Or you have like bigger cylindrical cells for the cost ratio, like the 46900 cells of Panasonic and Tesla. Or BMW will also use them. So you basically have different factors also on the cell design, which are updating. Obviously, they affect pack design. And then you have like basically like on the upper side, these new management systems that allow a longer cycle life, better usage also, new use cases that slowly appear because we get the first batteries back from first life. So there are many companies working on second life application and or recycling. and so on. So basically, these are the major trends on the different levels where you are, from really active materials to packs, and also to the final use case scenarios.
Well, thanks for this feedback. Do you see also major trends towards liquid electrolyte to more solid, depth like in between, semi-solid or things like that? Do you see that is coming in the near future, or that still takes time?
So yeah, the cool thing is solid-state batteries are the oldest batteries, right? So they are like 50 years plus old. I don't even know anymore like how old. They started in the 70s. So the solid-state batteries are now were always, like, when you look on patenting, they were always since the 90s. We only have overviews since the 90s. They were the second most patented technology since the 90s constantly. The first one was obviously liquid electrolytes, mainly additives for it. That are the most patented per year, a component in batteries from the cell components. And then only on level 3, that sometimes it's cathode, sometimes it was lithium air and sulfur. So it switches all the time a bit. Who's number 3? But number 1 was always liquid electrolyte. Number 2 was always like solid state electrolytes. And the challenges stay, it's like research, the challenges stayed like the whole time the same over these like 30, 40, 50 years. And the main advantage that we have today is that the interest is different. So we have a huge interest from the automotive sector, which means that there is a lot of money to accelerate this research. While we still face the same problems like 30 years ago, like contact problems of all solids touching each other, like if you have bricks touching each other, and they even have volume expansion, that's usually not going very well. While a liquid would always make the contact again, because one phase changes it's like liquid. That is the main challenge. But the cool thing is, with all this research that is done now, or this even, I would even call it new search, yes, we improve these batteries. But usually what many people underestimate is that batteries made it initially in the 90s, they made it only because we can scale batteries so nicely. Batteries can be scaled from tiny little coin cells that are smaller than your fingernail, like they are in watches and so on. They can be scaled up to big packs, like in trucks and buses. And that's the main thing why batteries became or lithium batteries became so good, because in the 90s we first started with small batteries with coin cells at Sony and so on. Then we went to the laptop cells, the 18650, which had fire issues initially and so on. And then we scaled them up to bigger packs and so on, and are now where we are now with the scaled electrolyte systems and so on. And the same most probably, and that's the fear that we have, that we always need to be cautious to directly jump from like lab test results or something to EV deployment of solid state. That usually takes quite some time. So will solid state come? Yes, they have been already there. The lithium polymer batteries in the 90s that have been in cameras and so on, they were already all used. And so on. That's these polymer batteries, basically, that lithium polymer and so on. But they need to scale slowly. So we will first see the solid state batteries in like special applications like drones or even phones or something, like goods where you pay a certain premium for the battery, because the battery is rather small, so you can pay double the price of it because it's anyway only $6, like in a smartphone, the battery basically. So you can pay also 12. It's not so much for the overall smartphone price. And then slowly scale to automotive. So will solid state come? Yes, they are already there, right? Since the 90s. But will they come easily to automotive? That will take quite some time and learning curves, I would say. Sorry for this long answer, because solid state is not the easiest one. It's quite complex, this one.
Yeah, I believe to create large format solid state battery cells is still quite challenging, right? And this
Yeah,
is
you have the
volume what you
change.
say too, right?
Exactly.
Yes.
So solid state is a big group, right? And once you use lithium metal, you have this huge volume breathing, it's called. The density of lithium metal is just 0.5 gram per cubic centimeter. So any milligram you deposit, you have like double the volume than water. So it's 8 times the volume than LCO cathode material, basically, when you store the same amount of charge. And that's the main issue. The density is so little. So many people just overlook. They look on milliamp hours per gram, but you also have to look on this milliamp hours per cubic centimeter. Basically, you just divide by the density. And then you see how much volume you need. And for solid state batteries with lithium metal as an anode, you have this insane breathing where this whole stack grows by 30% and shrinks by 30% and grows by 30%. So you have a very high energy density when you calculate it on cell level at discharge state, like when the lithium is all in the cathode. But once it starts breathing, you have a lot of problems in your pack, and you need to have where your pack can accommodate like breathing of 30% over a length of a 1.5 meter pack. So basically you have 30, 40 centimeter breathing in your car. And this is like very, very complicated where your pack, when you have all this high energy density on the cell level, but you basically lose it in the pack level again. That's like the complication in automotive.
Excellent. I saw before a question or Beat Rustaller, you raised your hand. Has your question already answered or not? I allowed you to use the microphone.
No, I think my question was not discussed yet. I was just wondering whether the lab test matrix aging data that you showed, whether there is suitable scaling laws available that can be applied and whether they are reliable to.
So yeah, you can.
They seem to be systematic. So is it possible to apply?
Exactly. Later on, usually when everything is good, then normal physics will apply, like Arrhenius law, or you can do Euler curves and so on. Exactly. So usually the nice thing is that, so I did not deep dive into that due to like the time that we wanted to, like for the presentation. But yeah, you usually have, so it's not like when you test the first battery that the second one with the same chemistry will be totally off. So yes, you will have first of all similarities between different similar LFP cells. You will learn that you may not need 9 SOC data points, but you need only 3 or 4, and that you need only like 3, 4 different temperature profiles, because there is scaling laws behind, like that are usually based on standard physics that we know, like Arrhenius for temperature dependencies, and SOC dependence is usually graphite based and so on. So yes, there exist repetitive patterns. And that's also what we want to help customers with, because if everyone goes through it, they all find these repetitive patterns like all together, right? And so that's what we usually want to help also there to show these different scalings and to derive the aging from it. Exactly. So there is, your answer, the short answer is yes, there are scaling laws behind.
Okay, thank you.
Let me see in the chat. There is a question from Marius. Have you developed some novel method to go through thousands of patents to get valuable information like software, or you still have to go one by one and read lots of them?
So yes, no, there is not yet. So for patents, it's very difficult to automate it, to automate the content, to make the search easy, so this is, there exist advanced search algorithms already, or like good search algorithms on the databases. But yeah, no, we still do it by hand. So when we have hits of like the highest 10, 12 patents, we unfortunately still need to read them, yes, and analyze them, because patents are also not written that you should directly understand what is inside. So they usually have relatively broad claims, and then you need to limit it down with your existing knowledge on other topics, what they actually wanted to do or which problem this patent is solving, because usually these patents are solving individual issues, or like patenting individual, like very certain aspects of, I don't know, a process, method of making or something like this. So yes, we do it still by hand with the trained PhDs that we have for this. Exactly. Yeah. Unfortunately, yeah, there is no machine solution. Would love to have it.
Well, if there is no further questions, let's give it a last chance. Then I would say, otherwise, thank you very much, Michael, for this insight. It was excellent webinar in the sense that we had lots of people. I believe this is also through your many followers that you have on LinkedIn. I guess you're the Swiss battery expert with the most followers in Switzerland. So this also comes back to the iBAT Association. So thanks to that. Thanks for your insight. As said, April 2nd is the next webinar from EcoVolta, and April 22nd is the next workshop on premise here at the Switzerland Innovation Park, BLBN. So I hope you will join that, and it's a good opportunity to see you face to face. So thank you very much, and hope to see you next time.
Thank you very much. It was a pleasure.